Common base amplifiers have some interesting quirks, so in this video we're going to look at a collection of 3 interesting facts about common base amplifiers. The first of these is that biasing common base amplifiers is more challenging than you'd expect. When you put a voltage divider on the base, it manifests in the small signal model as this R1 parallel R2 resistor connecting RPi to ground, which creates a voltage divider that means our value of Vin no longer directly controls VBE. Instead, VBE is controlled by a divider equation, which reduces the effect of the input and eventually reduces our gain. This is a great opportunity to represent this divider equation using our effective GM transform. You can pretend that our control voltage runs from here to here, and our GM instead has a resistor divider baked into it. But I won't chase that through here. A capacitor at the base can short out this R1 parallel R2 resistor in the midband, but that capacitor is prone to introducing instability in the amplifier for reasons we'll discuss later, so proceed with caution if you use one. In addition, if we need to bias the emitter of the amplifier, as seen down here, then that emitter resistor shows up as a current divider in our small signal model. You might be tempted to set RE to 0 and just hook a voltage source up to the emitter, but that would mean your input to the amplifier, your emitter, is small signal grounded, so that doesn't work. You might also be tempted to go the other way and let RE be as big as possible, or even an open circuit. But if you do that, then you have no DC path to ground through your emitter, and so the circuit doesn't work. So that means that RE usually needs to be not as large as you want, which affects your gain and input impedance. Second, though this is a bit of a detour, I wanted to show you this alternate way of analyzing a common base. We're not going to use it, but it's handy in case you see someone else use it in the future. So you can transform the small signal model of a common base by pretending that instead of current flowing directly from the collector to the emitter, you pretend that it flows to the base and then to the emitter. And we're allowed to do this because our models only capture the terminal behavior of transistors. They don't discuss what's going on internally, so as long as we have the same current coming out of the same terminals, any set of elements that we choose to draw inside of them is fine. Right, you might recall that this is already a transformed model from our original alpha model of the BJT. The GM generator between the base and the emitter is directly in parallel with its control voltage, which means we can just replace it with a resistor of 1 over GM. And we see that in the third subcircuit here. Collapsing 1 over GM and RPi in parallel reveals a surprisingly simple small signal model for common base amplifiers. The input voltage sees a resistor from the base to ground, which is RPi in parallel with 1 over GM, and that's often given the label RE for emitter resistance. Third, the current gain of a common base is about 1, which means you can think of common base amplifiers as current buffers. Said another way, any current that goes into them comes out from the collector, which is a high impedance source. So it looks as if you are copying any current that gets into them out through a current source. We measure current gain in a similar way to voltage gain as outlined up here. We imagine a Norton test current with infinite RS, so that's an open circuit, I haven't drawn it in here. And then we measure how much current goes through a shorted load attached to the output of the amplifier. We start our analysis by noticing that I out is equal to minus IGM, again presuming GM is flowing upwards in this analysis. And IGM is given by GM times minus VBE. Excuse me, and that IGM is given by GM times VBE. We then find VBE by writing KCL at the top node, noting that IN is equal to VBE over R pi minus GM times minus VBE. Rearranging this equation, we get this expression, which relates VBE to IN, so it's IN times R pi over beta plus 1. Substituting this back up here, we find that I out is equal to beta over beta plus 1 times IN. So the output current is almost an exact copy of the input current. So in summary, base bias in common bases causes an effective GM divider that reduces your gain. Emitter bias of common base amplifiers creates a current divider. That's annoying. You can analyze a common base by transforming the circuit into a T-model, and the common base current gain is beta over beta plus 1.